Well, if it's all right, then let me go back to the beginning, and if we run out of time, I'll just stop. Here, as I mentioned, is the roadmap that I had in mind. And so, because I have a very well-educated audience here, this should be a very enjoyable presentation. You know what we're talking about. So let's go ahead and talk to what dams do to water and sediment. Here's a rule that we don't seem to understand. Rivers are really very simple. They exist to move water and sediment downstream. That's why they exist. Now, when we build a dam, we interrupt things. We interrupt the transport of water downstream and sediment downstream in all of its sizes. So why build dams? Well, I hope we understand why. Here in the arid West, we have a lot of water. We just don't have it where we want it and when we want it. So we build a dam to store water so we can have it when we want it, and then with various canals, pipes, diversions, whatever, we can put it where we want it. Flood control is another huge thing that dams have provided for us. And if we didn't have our dams in the U.S., we would not be enjoying the standard of living that we do today. Put it shortly, okay? So obviously we need dams. But here's what we think about when we think about dams. This is a constructed dam right here. And we as engineers, we're a little bit obsessive compulsive, and we like things very well organized. And so when we build a dam, we have this mental image of different elevations within the reservoir. For example, down here, this is called dead storage. And that is the volume of the reservoir lower than the lowest outlet in the dam. This can be used for nothing. So it's called dead storage, and that's where we want the sediment to go. So when a dam is designed, the volume required for the sediment is estimated using about 50 years. And then the lowest level outlet is put above that storage zone. Then in the middle we have what's called accessible volume. This is where most of the water is stored. And then up here in this white zone, this would be flood control storage. So we really like to compartmentalize things, and that's how we visualize dams and reservoirs. There's only one problem. Nobody told the sediment that this is where it's supposed to go. And it doesn't really cooperate with us very well. So the reservoir fills up with water pretty quickly, unless you're on the Missouri River system. The largest storage dams in the United States exist upstream from here. So large that some of them would require 3 years to fill. 3 years to fill. In other words, the capacity of the reservoir is 3 times larger than the annual inflow, meaning that it takes 3 years to fill. Now, that's an extreme here in the United States. Gavin's Point could fill up 50 times a year, so its storage volume is much less. Now, if water fills a reservoir quickly, sediment fills a reservoir slowly. That's not always true, but usually. For example, if our sediment concentration in the water is 1%, well, there you go. You got 100 times more water than sediment. So what we have here, and academics like to describe this thing, is a slow and fast problem. And a colleague of mine who really likes math, he really likes math, he and I have published a couple of papers looking at the theoretical equations that govern fast and slow problems, and sure enough, we got a problem long term. I'd like to show you what the delta looks like in Gavin's Point. I first became acquainted with this issue when I was doing my PhD at the University of Minnesota. Did that work with Gary Parker, my advisor. I've been working on this ever since. What I did at the University of Minnesota, I had a small flume. It was only 6 inches wide. And I ran water down that flume, and this right here, this is my sediment. It's actually crushed walnut shells. Because the scale is so small, I had to use something very lightweight. So I used crushed walnut shells, bought them by the bag, 50 pounds in a bag. And I fed them into the water. Now, when I began this experiment, the water was very shallow, but I put a dam in the way, and that backed the water up. It backed the water up from here to here. The sediment just kept on coming, kept on coming. Well, there wasn't enough energy in the water to move the sediment, so it drops out immediately, right there, right at the beginning of my reservoir, and just builds and builds and builds and builds until the velocity across the top of my sediment is sufficient to move the material downstream. So what happens over time? That delta moves downstream into the reservoir. And this would be the coarse material like sand. So let's take a picture of the river before and after the dam. Here is the river and the sediment bed level before I made my little dam. Here it is afterwards. Ultimately, that's what a reservoir looks like when filled with sediment. The elevation, I hit the wrong button. The depth of water over the deposits is just what it was before the dam was built. We've just raised the ground a distance equal to the elevation of the dam. Now, this is for coarse material, sand. What about the finer material? The finer material, if this is the sand, and this is what we've got in Gavin's Point, the finer material goes on downstream and can settle out along the way, or the very fine stuff will actually dive into the reservoir and become a submerged river of its own. That fine sediment and water hits the dam, rebounds back, and makes muddy deposits right at the dam. Not very much of that going on at Gavin's Point. But that's the process of sedimentation as seen from a side view in a reservoir. This is the most complicated thing I'm going to show you today, and I'll explain to you what I'm talking about. Of all the sand that comes into Gavin's Point Reservoir, how much drops out versus how much passes the dam? Well, we know the answer to that question, and the answer is 100% of the sand drops out. And so that's called trapping efficiency. How efficient is Gavin's Point at trapping sand? 100%. But for the very fine material like colloidal clay, some of that will just pass right through. That's the muddy water that we see, but we don't often see it on the Missouri anymore. So this is a graph whose x-axis is how big the reservoir is. And the largest ones on the Missouri are up in this range, where it takes 3 years to fill. Notice that there aren't many dots up here. Each dot represents a dam. And on the y-axis is this how much sediment is trapped. Well, you can imagine with a huge, huge reservoir like in North Dakota, all the sediment drops out. But with a very small dam, some of it can pass through. So this is called trapping efficiency. And engineers used this when they designed dams. Now we use it to try to manage sediment. All right, now I want to get a little bit philosophical here and share with you a couple of quotes. When did we know that Gavin's Point was going to act like it does? When did we know that dams were going to fill? This quote about Boulder Dam, renamed Hoover Dam. This is from J.C. Stevens, worked for the U.S. Geological Survey. He said, unless remedial measures are adopted, this reservoir, meaning the one down by Las Vegas, will become virtually useless by the 5th generation. What a forward thinker he was. When dams have been designed in the United States, we weren't looking at the 5th generation, or the 4th, or the 3rd, or the 2nd. We were looking at ours. That's how they were designed, and I'll explain that more later. But he was very forward-thinking. He said, fortunately, sites are available where other reservoirs may be constructed, and they were on the Colorado River. 2 dams upstream. And after these are gone, others will doubtless be found. But what says Stevens of the ultimate future, when all available storage sites have been exhausted? Must these fertile areas revert ultimately to the sagebrush and the cactus? Will sedimentation that made possible this vibrant civilization ultimately sound its death knell? Well, that sounds pretty depressing. Look at the date, 1936. He continues, it's not the writer's intention to paint a dark picture, but rather to stimulate a more intensive study and an intelligent research that will ultimately affect a practical solution. The menace exists. It is real. It is unfair to pass this problem flippantly on to future generations. This is my major research area. What we can do about this. And as I teach my students, I tell them, you're going to solve this. We're coming up with the techniques now. You're going to see them to fruition. Now, that was in 1936. In 1975, Bondurant, who worked for the Bureau of Reclamation, said the following: considering the limitations of current technology, it must be recognized that with few exceptions, ultimate filling of reservoirs is inevitable and must be taken into account in project planning and design. It's not been taken into account in project planning and design, and it's not inevitable. He also said, in an age that has progressed from the first automobile to a landing on the moon in much less than a 100-year span, it's possible that in time either the reservoirs of today will no longer be needed, or that more effective methods of retaining the capacity will be developed. However, until then, it will be necessary to carefully analyze the sedimentation characteristics of reservoirs to ensure their continued functioning. This last sentence is just now being adopted by the Corps of Engineers and the Bureau of Reclamation, the 2 biggest federal agencies who own dams. We've known about this for some time. Okay. Now, I'd like to talk for a few minutes about impacts that dams have. And I think you're well versed on this, but this one you may not be as familiar with. This is from a drawing in 1953. This shows a dam and a delta composed of sand, coarse material. This is Gavin's Point. What isn't as well known is that this delta moves upstream as well as downstream. Because as sand drops out, the water gets a little bit, the water level rises a little bit in order to move sand across it. And then sand can drop out just a little bit farther upstream, and the water will rise because the stream bed is higher. And on and on and on. 1953, before Gavin's Point was built. This is Qasem El Ghirba Dam and Atbara River in Sudan. I've been there. This is what conditions look like at the dam. This is what your ministers of agriculture and irrigation see when they visit the site. This is upstream, 70 kilometers upstream from the original reservoir. 12 meters of deposition. This is a water pumping station. Those intakes are 40 feet below the deposits. And this is upstream from the original lake.
What was the time frame?
About 20 years. Sediment loads in Africa are unbelievably large. This comes from Ethiopia and they get it. Niobrara, as you well know, has been moved twice. This may have been from the first move during ice jam flooding, but this is the more recent move, and we've got some folks from Niobrara here today. Those are upstream impacts of the original reservoir. Now, why is this? You might recall that I showed you this idealized picture of how engineers used to view the world, and we want all the sediment to go down here in this dead storage area. Sorry, that's not what happens. This is an aerial view of Millsite Reservoir in Farron, Utah. This is the dam. Here's the reservoir. Dead storage is located right along in here. Is that where the sediment is dropping out? And if you fly on a clear day from X to Y, just take a look at any dams you see from the air, and you'll see where the sediment drops out. So impacts within the reservoir include sediment dropping out in this active pool. This is where we want to use the water for irrigation, for recreation. We want to use it, but this is where a lot of the sediment is being stored, and we lose access to that water. Also, within the reservoir, the Bureau of Reclamation is mostly concerned with gate blockage, impacts on outlet works like sand abrasion on turbine blades, things of that nature. Obviously, in-reservoir impacts include recreation. It's not all bad, though, because at the upper end of Gavin's Point, Lake Lewis and Clark Lake, you've got great upland bird habitat. It's fantastic. Great hunting, fishing up there. So it's not all bad, but within the lake, in Yankton here and in Niobrara, reclamation is impacted. How about downstream impacts? This is something you may not have thought of a lot because it's so obvious what you're concerned about here. But those include streambed incision that precedes up tributaries, banks, channel widening, impacts on infrastructure. Here's a small-scale example. The lower Elkhorn River in Nebraska, not too far from here. The dam is about 5 feet high. And as we look at the bed and banks upstream, notice how well vegetated and stable they are? These are what the banks look like downstream. What's going on? Well, when sediment drops out, clearer water is discharged from the dam. That water has more energy than it did before. It's kind of like a teenager with a car, or a teenager in a grocery store with mom and dad's credit card. They just buy up everything they can see. Lots of energy. It's called hungry water, and it will pick up sediment from the stream bank and beds. And there you go. The banks become unstable and collapse into the reservoir, into the river. Now, in an interesting case on the Rhine River in Germany, this is a barge. The barge comes through several locks and dams from upstream. By the way, those locks and dams are catching all the gravel in the Rhine River. We're not talking about sand now. We're talking about stuff the size of marbles and golf balls. It all drops out upstream. The Rhine River downstream was attacking its banks looking for sediment. So on the Rhine River, 24/7, never stops. Gravel is taken out in the middle of the river and dumped. Just dropped. So the river has something to carry instead of attacking the bed and banks. That's the Rhine River. Now, in our own neighborhood, right here, the x-axis is 1960 river mile. So where are we? Here's Yankton. And see these different lines here? You've seen these before. These are the stream bed levels. Stream bed level now at Yankton, at least at that time, was about 1155. It used to be about 1163. The stream bed of the Missouri River downstream from the dam has dropped 8 to 10 feet. Now, the issue with that is, if you're a tributary that comes into a river and the river level drops, what's the tributary going to do? the tributary is going to drop. So in eastern Nebraska, western Wyoming, those loess-based rivers are unraveling west and east because the stream bed on the Missouri has been dropping. So those are some downstream impacts. This is a drawing that represents, this is the Gulf of Mexico, this is the Missouri River, this is the Mississippi, this is New Orleans. The figure on the left, around 1800, is the sediment load that used to come down. The figure on the right, 100 years later, is how much sediment is now coming down. It's been greatly diminished. Diminished by at least two things. Dams, there's dozens of them now constructed upstream, not only Gavin's Point, but many others. And soil loss reduction. That's a good thing. We're now eroding less soil from our farmlands. Less sediment moving downstream, what does that mean? Well, let's look at the Nile River. The Nile and its rich delta is shrinking. With the construction of dams upstream in Egypt, the Nile no longer floods. It doesn't get out of its banks every year, and for thousands of years it did. And the silt it was carrying, deposited in the floodplains, the waters receded, the farmers used that fertile soil to grow crops. The water no longer floods. It's clearer. And when it gets down to the delta, it finds an ample supply of sediment and it erodes it. A local industry there at the mouth of the Nile used to be making bricks out of these deposited sediments found in the delta. It is now against the law to do so because the delta is shrinking. The Rio Santiago in Mexico I visited several years ago, a major river in Mexico with a coastal fishery. The construction of dams upstream has stopped the sediment movement to the mouth. The stream bed is degrading, and in this case, these are endangered mangoes, a mango swamp, and all the habitat, animals, birds, bugs, fish that go with it. And the Mississippi River, you're familiar with this one, how the delta at New Orleans has been shrinking. Not only has it been shrinking, it's sinking. So it's kind of a double blow down there in the delta. Shrinking and sinking, it's shrinking because the lack of sediment supply from upstream. And that has big impacts on infrastructure, from oil rigs to the protection of New Orleans. So on a cosmic scale, on a bigger scale than our local issue here, are impacts of not managing sediment on downstream waters. Okay, Sandy, are we doing okay? Should we take a little break, or what would you like to do?
Let's take 5 minutes.
Okay, great.